Hi everybody, welcome to Physics 307. This is the photoelectric effect lab. So, in the late 1800s, physicists discovered that if they bombarded a surface, a metallic surface, with light, then electrons were emitted from that surface. And they discovered a few really interesting things about that phenomenon. They discovered that it was very frequency dependent. So the energy of these electrons was dependent on the frequency of the incoming photons. They also discovered that below a certain threshold of frequency, that there was no emission. So if you went to too low a frequency, you didn't see any electron emission at all. So you ended up with a plot that looked something like this. On my y-axis, I put a photocurrent, which would be the photocurrent is equal to the charge over time. And then I looked at frequency. I'd see something like this. With a cutoff frequency right here. And this was really weird. Nobody understood why we should have this sharp cutoff. We also discovered that that this process was intensity independent. If you were below this threshold, no matter how much light you bombarded onto that surface, there would be no photocurrent if you were below that threshold. So this was a real mystery. And then Einstein came along and gave us this formula, that the kinetic energy of these electrons is equal to the energy of the photon minus some work function, which would represent the binding energy of this material or incident. And this was completely revolutionary because it was one of the first applications of Planck's constant, which depended entirely on the photon having a quantized energy. So this really blew the community away, but it perfectly describes the behavior. So, we have the photoelectric effect. What are we going to do with it? So what we're going to do in this lab is we are going to use the characteristics of the photoelectric effect to measure Planck's constant over the charge of the electron. So this is the fundamental constant that we are after. Okay? And the way we're going to get there is by setting up our experiment like this. We're going to set up an electrode, and we're going to set up a plate. Okay? And so we're going to have photons incident on this plate. And electrons are going to come off of that surface. And hit the electrode. And again, this is going to generate a current. Equal to the change in charge over the change in time. Now, okay, so what does this tell us? We can easily use this to discover the concepts of the photoelectric effect. And we can easily use it to regenerate this. But in order to measure this constant, h over e, we're going to do something a little different. We're actually going to try to stop these electrons from reaching the surface. And the way we're going to do that is by applying a voltage between the electrode and the plate. Now, why would we do that? Well, to stop these electrons from reaching the electrode, we need to do some work. And so if the electrons have energy Ke, in order to stop them, we need to do work equal to Q times V. Okay? In order to stop it completely, we'll have this equal to 0. Right? So now, plugging in our relation for the kinetic energy as described by Einstein, we have h nu minus the work function phi is equal to the charge of an electron times v. So I should write these consistently. Okay, so this is what we're after. We call this voltage where there's no current in the system to be the stopping potential. So let's talk a little bit about what we're actually going to see in this experiment. So we have our kinetic energy relation here. So h nu minus a work function is equal to the charge of the electron times the stopping potential. And this relationship only holds at 0 current. Okay, otherwise the electrons have some kinetic energy and you'll see a current on your meter. So we have this, we have our plate, we have our electrode, we have incident photons and electrons hitting that electrode. And we're trying to stop those electrons with this potential. So, just looking at this, we should be able to look for a 0 current point and just call it a day. Unfortunately, we cannot do that. So here's our circuit. So we have attached to this an electrometer. An electrometer is a very sensitive device used for measuring very small currents. And these are small currents. In this lab, we're going to be dealing with stuff on the picoamp level. So, we'd like to just be able to look at the 0 point on that and say, well, okay, that's the point where we have a stopping potential. So we can scan our voltage and then look for 0 current and say, okay, stopping potential is right here. Unfortunately, we can't do that because in addition to these electrons, there are all sorts of background electrons floating around. Some of those electrons are due to light hitting the electrode and electrons being kicked off of that. So that's a reverse current that's coming from a completely different source. So we have to be a little more careful than that. What we're going to see as we scan voltage, I'm drawing this way because we're actually going to scan our voltages from a more negative voltage to a less negative voltage. And what we're going to see is as we decrease the voltage, the kinetic energy of the electrons is going to increase, so we're going to see something like this. We're going to see this current decrease that's solely due to, it's not due to the photoelectric effect at all, it's just due to accelerating background electrons into the anode. And then we're going to see the photoelectric effect kick in. Okay? So, this 0 point of current isn't an accurate gauge. In fact, this whole Y scale isn't terribly useful. However, what we do have is we do have this sharp turn on, the photoelectric effect, coming to rescue us here. So what we can do is we can say, okay, well, if we fit a line to this, okay? If we fit a straight line to this, which is solely due to our potential, and then look for deviations from that line that will be due to the photoelectric effect, then we can say, okay, well, our point of interest, our point where we have a stopping potential exactly, is going to be this inflection point in voltage. So this value right here is going to be our stopping potential. Okay? Now, this experiment is really a challenge. Again, you're dealing with very, very small currents. Anything you do in the room is going to affect your result. If you have very small currents, then any capacitance you have is going to affect your results. So wiggling wires, breathing on the apparatus is really going to throw off your results. So you have to be very, very careful. You're going to start off with pretty low gains on the electrometers. But to get good results, you're going to need to go to very, very high gains. So you're going to start off with this electrometer looking at nanoamps. But in order to get a good result, you're going to have to really kind of zoom in on this portion of the curve. You're going to have to go to the picoamp level. And that's a real experimental challenge. But if you put the time in, you can get a very, very good result. So that's the Photoelectric Effect Lab. I hope you'll contact me if you have any questions about it. Thanks.